lecture is for a very special kind of functions for optimization, that is on the convex function. This class of function is really special in optimization because you will find that wheresoever there is a minimum point of the objective function or the function that you wanted to minimize, wheresoever there is a local minimum here or here, you will find that wheresoever there is a local minimum locally, that is in a neighborhood of the local minimizer, you will find that the surface of the function looks like a bowl type surface. This bowl type surface is called a convex function. So if you want to analyze even a local minimizer, or even if the function is not convex, then you have to analyze in a local neighborhood of the minimizer, and hence you have to analyze the function, the surface of the function that looks like a bowl type surface. And in this lecture we are going to describe a special kind of characteristics of this kind of functions, the convex functions.
In the last lecture, if we try to visit our class note, we shall find that in the last lecture we were trying to discuss about theorems of alternatives, where precisely two systems were given and only one system will have a solution, not both. And towards this, the Farkas lemma was derived. Geometrical fact in the Farkas lemma was given, and afterwards, as a corollary to Farkas lemma, we have derived the Gordon's theorem, as well as two other corollaries to Farkas theorem was given, and those two theorems will be helpful in deriving the necessary and sufficient optimality condition for a constraint optimization problem. The popular Karush-Kuntakar condition will be developed with the help of the two corollaries, last two corollaries that we have derived on the last day. Well, in this lecture, we will try to discuss about convex functions. We will at first define what do we mean by a convex function, as well as we will define what do we mean by a concave function. Two special types of convex functions also will be defined. Those are strictly convex function and strongly convex function. As well, after defining the convex functions, strict convex functions, as well as strongly convex function, we will try to discuss several properties of convex function and several characterizations: zeroth order characterization, first order characterization, and second order characterization of a convex function will be given. Well, so let's start our class with the definition of convex functions. Before getting into the definition, let me speak a few words why convex functions are important and why optimization problems involving convex functions are truly important. You know, in convex optimization problem, or in the objective function of a convex optimization problem, which is obviously a convex function, has three most fascinating properties regarding to optimization. Those are: any local minimum of a convex function over a convex set is also a global minimum. The second one is any stationary point. By that I mean a point for which the gradient or the derivative of the function vanishes of a convex function must be a global minimum. Any stationary point of a convex function is a global minimum. And the third property is very important and much more fascinating, is even if the function f is a given convex function, f is, even if it is not differentiable, but still it will have a directional derivative. Most fascinating. Any given convex function, you take any interior point of the domain of the definition of the function. At that point, along any direction, the function must have a directional derivative. Well, so these three properties, although in this lecture might not be possible to derive all of them, but in the next lecture, by this lecture and the next lecture, we will try to see how directional derivative, as well as the other two properties, local minimum implies global minimum and stationary point is a global minimum for a convex function, how those are coming out. We will try to derive them. Anyway, so let's start, and possibly for these three properties, convex optimization is richer than any general non-convex problem. Well, so let's start our class with the definition of convex function. What do we mean by a convex function? By a convex function, we mean the following. A convex function is always defined over a convex set. So we let capital S be a non-empty subset of the n-dimensional Euclidean space, and f be a function defined on the set, a real valued function. This function f is said to be convex on the convex set S if the following property holds. If you take any pair of points x1, x2 belonging to the convex set S and corresponding to any lambda in between 0, 1, you consider the convex combination of x1 and x2, the functional value at the convex combination lambda x1 plus 1 minus lambda x2 is lesser than or equal to the function value fx1 times lambda plus 1 minus lambda times fx2. If this inequality happens for any pair of points x1, x2 in the set S and for any lambda in between 0 and 1, then we say a function f is convex. Now, what is the geometrical essence of this definition? For the geometrical essence, we note the following. What does this inequality mean? It means that whatever point x1, x2 you take from the domain of definition of the function, let's suppose, let me explain for a function of one variable. Let's suppose this is my function value axis, capital Y, and this is my real axis. And here goes the set. Let's suppose the set capital S is this interval from A to B. Now the definition of convex function says that you pick up any pair of points. Let's suppose I pick up x1 here, x2 here, and then you consider a convex combination. Let me suppose this is my considered convex combination. Any convex combination of x1, x2 you take up, lambda x1 plus 1 minus lambda x2. Fine. And the function value at this point is below the value lambda fx1 plus 1 minus lambda fx2. We note that this expression is nothing but the chord. It finds the chord joining the points x2 fx2 and x1 fx1, x1 fx1. Fine. Now you consider the chord joining these 2 points. We note that obviously then this point, as this graph is a line segment, this point obviously, this particular point obviously is having coordinate. The x coordinate is lambda x1 plus 1 minus lambda x2, and at this point the function value is obviously, this is the function value lambda fx1 plus 1 minus lambda fx2. Fine. And what does this inequality mean? The value of the function f is lying below this particular value on the chord, and this is going to happen for every particular convex combination. You can take here, you can take here, you can take here, anywhere you take, and accordingly observe that the function value must be below the chord joining below the line segment, joining x1 fx1 and x2 fx2. And accordingly, you will find that it will trace out a graph like a bowl type graph. Fine. Bowl type why? Because here you note that corresponding to the considered 2 points x1 and x2, considered corresponding to x1 and x2, the graph is lying below. And not only corresponding to this x1 and x2, you vary the points x1 and x2. Let's suppose I vary the points, these 2 points, let me consider, and accordingly the graph must be lying below this chord. Similarly, if we consider, let's suppose I consider another 2 points. Let me consider this point and this point. The graph of the function must be lying below this chord. Graph of the function must be lying below this chord. Graph of the function must be lying below this chord. And accordingly, we note that obviously then the graph of the function must be having a figure like this parabolic type. Fine. And therefore geometrically this inequality signifies that the function value at any point lies below the function given by the chord joining the 2 points x1 fx1 and x2 fx2. Fine. Or much more loosely, if we try to speak a convex function, the graph of the function lies below the chord joining any 2 points on the graph. Fine. This is for the geometrical significance. Let me define here what do we mean by a concave function. If minus f is convex, then we say f is concave. Fine. Now here, if the inequality, this less than equal to sign, if this less than equal to sign goes with strict inequality, then we say the convex function is a strictly convex function. By strictly convex function, we mean a function for which the inequality, let me name it as 1, is strict on the convex set S. Why do we care about strictly convex function? Because strictly convex function possesses two special properties. Those two special properties are the following: that for a strictly convex function there can be at most one global minimum, and therefore once there exists a minimum of the given strictly convex function, then that particular point is a unique local, indeed global minimum of the given function, and therefore there can be at most one global minimum of a strictly convex function. Not only this fact, there is also another important fact that we shall learn later, that differentiable convex functions are closely related to positive semi-definiteness of the Hessian matrix. And for a strictly convex function, we shall see that Hessian matrix at any point on the domain of the definition must be positive definite. Once the Hessian matrix is positive definite, it must be invertible. And once it is invertible, the fastest known method in optimization, the Newton's method, will work well for the given objective function. And therefore, if the objective function of an optimization problem is strictly convex, you can apply the fastest known optimization method, the Newton method, to solve the given problem. Due to these two facts, we do care about strict convexity. And for convex functions, I have already mentioned, we do care about convex functions because of local minimum will imply a global minimum, stationary point will be a global minimum point, and also it has directional derivative at any interior point on the domain of the definition. And for faster rate of convergence of a given optimization problem, we also do care about another notion of convexity, that is the notion of strongly convex function. By a strongly convex function, we mean a convex function which is convex or curved at least like a parabola. Let me define what do we mean by a strongly convex function. By strongly convex function, we mean that if the function fx minus a positive constant times, here c is a positive constant, if c by 2 norm of x square is convex, then we call f as a strongly convex function. We note that this means, although we may derive later on, this definition of strongly convexity essentially is equivalent to the following: that if f of lambda x1 plus if there exists a constant c such that f of lambda x1 plus 1 minus lambda x2 is less than equal to lambda times fx1 plus 1 minus lambda times fx2 minus half of c lambda times 1 minus lambda norm of x1 minus x2. Fine. Here note that we have seen that this expression on the right hand side is a linear function, right? Precisely, it is the chord joining the points x1 fx1 and x2 fx2, and therefore it is a linear function. It is a linear function, and this part is a parabolic function. This part is a parabolic or quadratic. Fine. And therefore, what does it mean? It means that a function is strongly convex if not only it lies below the chord joining any pair of points, but also you consider any given point, and at this point you will find that there is a parabola that lies below the graph. Fine. And we also will see, if a function f is differentiable, then at any given point on the graph of the function, if the function f is convex, then there is a supporting hyperplane. By supporting hyperplane, obviously we mean a plane that touches the given graph of the function. If a function f is convex, then we will find that, and convex, and if it is differentiable, then we will see that precisely the tangent at a given point, let's suppose the given point is x bar, at a given point x bar, the entire function lies above the tangent on the graph at the point x bar, and therefore this tangent line gives a lower estimate of the entire convex function. We note that the expression of a given function in an optimization problem is not easy to find always. By that, what do we mean? But there I mean, we know that in our classroom problem, we always do consider functions with exact expressions. For instance, I can take a function of, let's suppose, e to the power minus x or x log x, whatsoever function you can take. Here you note that the function's expressions are explicitly given, but in an optimization problem, it is not always easy to find the exact expression of the function in terms of the variables. In practical optimization problems, it is not an easy task. You know that in your laboratory, you do several experiments with several parameters, and after devoting a lot of time, you get certain number from your machine. These numbers are precisely the function values. So several inputs you are giving, then you are devoting certain amount of time. This time can be hugely big for practical problems, and afterwards you are getting a output as a number, that is your function value. And therefore you give several inputs are here your variables, and after that you devote a time, then you get a numeric value of the function. And therefore for different inputs, different argument points, you are getting different numerical values of the function, right? And therefore for different points you are getting, let's suppose, different function values. Accordingly you can get an approximate idea what is the graph of the function at most. If it is a function of two variable or it is a function of one variable, then you can get a graph. But for function of three or more variables, approximate graph is also not possible. And practically in an optimization problem, the number of variables in practical optimization problems, they go beyond billions. It is not like three or four variables you get. For instance, you take support vector machine problem in machine learning. In this era of big data, you will find that the number of function values and there are number of inputs, those are hugely big. They move more than billions. And how do we find them? How do we imagine? How do we estimate that what could be a local minimum? What could be a possible global minimum of the given objective function? It is really a difficult task. And therefore, here somehow, depending on the numeric values of the function, if you somehow get an approximation of the derivative of the function, that is precisely the slope of the tangent. And if you get the derivative, you know the tangent on the graph, right? And if you get the tangent, what does the convexity imply is that at any point x bar, tangent gives a lower approximation of the graph. That means you are for sure at any point x bar you get the tangent. The tangent expression does not depend on the expression of the function. The tangent's expression, as you all know, that this depends on the function's value and the derivative value of the function. As you all know, in general, for function of several variables, the tangent's expression goes like fx bar plus gradient fx bar transpose x minus x bar, right? And here you note that you know the point x bar, you know the derivative value somehow. Depending on the function values, it is possible numerically to find the derivative values, and here you know the function value. So depending on the function value, if you can somehow estimate what is the derivative value of the function, then you get an estimate, a lower estimate of a convex function. Any convex function you consider the tangent at any point x bar, the function value can never come below this tangent line. The function value can never come below this tangent line. It is happening at any point. You consider any other tangent. Let's suppose I consider the tangent at this point. This is happening the same fact that function's graph lies above the tangent line. Fine, and therefore tangent line on a convex function gives a lower estimate, a global lower estimate. Global lower estimate, why? At any other point x, you consider the function value of the graph, the function value always above this tangent line, and therefore tangent line is always a lower estimate of the graph of a convex function. And for strongly convex function, there is a parabola that is a global lower estimate of a strongly convex function, and that is what the right hand side says. This right hand side here, you know that this right hand side on defining the strongly convex function, this right hand side, you note that this right hand side is precisely a parabolic equation. From here we can derive this fact from this inequality, that if there exists a c greater than 0 such that this is happening, this has to happen for all x1 x2 belonging to the convex set S, and as well lambda belonging to 0 to 1. Fine. If this is happening, then we can prove that there is a parabola at any point x bar which touches the graph at the point x bar and which is a global estimate for a strongly convex function. So the geometrical significance of strongly convex function is that it is a convex function that is convex or curved as good as, at least as good as, like a parabola. Fine. Well, so with this idea, although we'll prove this fact later on, both the facts. For a convex function, the tangent line gives a global lower estimate. For strongly convex function, there is a parabola which gives a global lower estimate of the function. Fine. Anyway, so with this, let me move ahead to give you a hierarchy between the three concepts. The three convexity ideas that we have defined till now, those are convex, strictly convex, then strongly convex. Let me try to pose as a question that is every convex function strictly convex? Obviously, your answer is no. And if no, I will ask the reverse question: is every strictly convex function a convex function? And further ahead, is every strongly convex function is a convex function? Is every strongly convex function is a strictly convex function or not? Here, if you are saying that convex function might not be strictly convex, for that you need to give an example. An example you can construct very easy examples. Like here, you note that let me tell you a simple fact about convexity, strictly convexity, and strongly convexity. For convex function, you note that convex function will have a graph like a bowl type, or it is like you take a string and fix the end points of the string and you hang over, and accordingly you get a curve like this is a curve, and for this curve whatsoever chord you take up from here to any other point you join, the graph of the function obviously lies below the chord, and therefore this is a convex function. Now here you note that if a function f is convex, you can have the following fact, that it can be a graph like where the function is constant in between certain points. This can be possible. For strictly convex, this constant value of the function in an interval is swept away. It is not possible for a strictly convex function. And for strongly convex function, here at any point you must have a parabola, and therefore again what will happen for a strongly convex function? Obviously you cannot have a constant like figure, constant value of the function in a given region, in a given interval, or in a given region of the domain of the definition of the function. Fine. Therefore, you can intuitively find that strongly convex will imply convex, and eventually from this inequality also this follows. This inequality, here you note that on the strongly convex function, here you note that the expression on the right hand side is always less than equal to lambda fx1 plus 1 minus lambda fx2, and therefore strongly convex function is a convex function. And why less than equal to? It is strictly less than lambda fx1 plus 1 minus lambda fx2 because c is a positive constant, and therefore what will happen? A strongly convex function is always a strictly convex function, and a strictly convex function obviously by definition it is a convex function. However, the reverse are not true. Convex functions might not be strictly convex functions, strictly convex functions might not be strongly convex functions. Let me give you example for each of the case. That a convex function that is not strictly convex is a function like the graph that I have drawn over here. Let me give you a mathematical expression, because this course must go with mathematical flavor. So every abstract graph that you are thinking, that should be mathematically presented. Let me give you a function like this. You please quickly on your own just draw out this function, and you will find that it is a convex function and it is not a strictly convex function. And for a function which is strictly convex but not strongly convex function, for this you will have an example, this example, that fx equals to the power 4. The graph of the function x to the power 4, this graph is lying above the parabola, right? This is your parabola x square, and the graph of the function fx equals to x to the power 4 gives a figure like this. This is your fx equals to x to the power 4. Fine. And here this function fx equals to x to the power 4 is a strictly convex function, but here it is not a strongly convex function. And why not strongly convex function? For that we need to derive a little. Although there is a parabola lying below the graph x to the power 4, but still this is not a strongly convex function, because we will learn later, for a strongly convex function the second derivative value of the function must always be greater than the constant c. The constant c is over your in the definition of the strongly convex function, and this c is a positive quantity. And but here for this function fx equals to x to the power 4, we note that f double dash at the point 0 is equal to 0, and that's why this function fx equals to x to the power 4 will fail to be strongly convex. Well, this is much about the definition of strongly, strictly, and convex notions. Now, let me move forward with precise examples and precise theorem derivations. Let me give you several examples commonly occurring convex objective functions in optimization problems. The examples that I would like to enlist are the following 10 examples. The first one, any norm, you take any norm, it can be L1 norm, it can be L infinity norm, it can be L2 norm, any norm, whatsoever norm you take any function that satisfies these three properties, this is a norm, and norm is always a convex function. This is due to the following fact, that norm of lambda x plus 1 minus lambda into y, you will have this is less than equals to lambda x plus 1 minus lambda into y norm of it. Find triangular inequality, and this will give us, as lambda is a non-negative quantity, lambda times norm x plus 1 minus lambda times norm y. Fine. And therefore any norm is a convex function. And as well, let me also mention the ellipsoid norm, or the Moholy-Neves norm, or Moholy-Neves distance from origin. This was derived by P.C. Moholy-Neves in 1936 for statistical theory to measure distance from a point P to a distribution, and this was given by norm of x, where q is a positive definite and symmetric matrix. Q transpose is equals to q, obviously of order n by n. Here q is of order n by n because we are working in the n-dimensional Euclidean space Rn. Then norm x subscripted q, which is also called ellipsoidal norm or Moholy-Neves distance from origin, and this is given by positive square root of x transpose qx. This is also a norm that we can just verify that all the three properties they are holding true. And as a norm is a convex function, therefore Mononomic distance or ellipsoid norm is also a convex function. Fine. Well, so let me move ahead to give you the next example. Let me consider a few functions of one variable. Quickly, let me consider exponential function for any a you take in R. This function is a convex function, and that is a function of one variable we are considering here. So you can quickly just graph out and check. Here, checking convexity is not an easy task always, but for function of one variable, just quickly graph out and check the convexity. If a is a positive quantity, then you note that the graph of e to the power ax will look like this graph, and obviously this is a bold type graph. Any chord you consider and the graph lies below the chord, and therefore this is a convex function. This is a graph of e to the power ax for a given a greater than 0. Fine. And for e to the power ax, when a is less than 0, we'll have graph like this: e to the power ax with a less than 0. Fine. And these two graphs quickly gives you a feel that obviously the function e to the power ax is a convex function for any a in the real number line. Let me give you another few examples. Exponential function, again we consider the exponential function of this type, x to the power a, and here a should not be any real number. A should be restricted by for a greater than equals to 1 or a is less than equals to 0, then only it is a convex function. Now the next example includes negative of the logarithm function, and this function is a function again of one variable and on the positive real number line. This is also convex. However, here you note that if we take log of x, this is then a concave function, right? And then let me consider the negative entropy function. In information theory, people do use quite frequently. This is given by x log x. On the positive real axis, the function is a convex function. You can just quickly graph out and you will find that I have drawn this graph a priori. Let me give you the graph of this function. This graph will look like this, right? Although it will not touch 0, and it has a global minimum at this point 1 by e. Anyway, then next let me give you a function of two variables, x1 square plus x2 square minus x1 into x2. Here let me put 2 into x1 square plus x2 square minus x1 x2. And here for this function, if you try to check with the help of the definition, it will be a disaster. It is not that you will not be able to find, you will be able to find, but you will, if you try to verify the convexity of this function, even for this simple expression of two variables, you will find how much messy the calculation will be. It will be very tedious one. And with the help of the theorem that a function, if it is twice differentiable and if its Hessian is positive semi-definite, then the function must be convex. You can find that for this function, which is a quadratic function, its Hessian matrix is positive semi-definite, and therefore this function is convex. Although we'll derive this result that if a function is having positive semi-definite Hessian, then the function must be a convex function. We'll derive several characterization, first order, second order, as well as zeroth order. Anyway, so let me give you another few functions of several variables. Any affine function is always a convex function. By affine function, I guess you all are familiar by now. Affine functions are given by a vector vector transpose x plus a scalar b. Affine function is not only a convex function but also it is a concave function. Can you be able to prove this fact that a function, very interesting, let me give you as a home task. It is little tricky, I should not have given home task here, but the point, our time is limited. Within 40 lectures we have to finish a lot of agenda. I will try to discuss as much as possible by 40 lectures, and somehow I want to give you a flavor of research in this course. Several PhD students and obviously brilliant you people are there. Once you have opted for optimization, I hope that you are interested in optimization theory, and therefore, being a teacher, this is my prime duty to inform you as much as possible. And for proofs and all, if you have a little bit of time, when you will have ample time, not in between during this course, might be later on when you will be involved with optimization theory, if you need someday, during that time if you need certain proofs, you can just have a look. For the proofs, do not worry about, I will always give you not only hints but also I will give you references, precise references from where the proof can be found. And therefore you don't need to be hang around the proofs now. If I find some theorems are important, so obviously, as this course should go in mathematical way, I should give you mathematical proofs that are difficult to understand, but for easier ones, which I will feel that you people are brilliant enough to understand on your own, I'll just skip them out. Few proofs are tricky, but I will skip for you, so that if you try to hang around that particular proof, then you will find that it is interesting. Fine. So several trade-offs are there. Trade-offs are the following: as you people are engineering, some of you are engineering students, some of you are mathematics students, some of you are even from biomedical also, I observe some people are there. Anyway, so here, I should make a proper balance between theory and methods. If I go much deeper into theory, some student will not be able to find it is easy course. Although it is a task of teacher to make the things easier, but also you know that it is also a task of the student to at least devote a little bit of time. If you don't devote any amount of time on this course, it is not always possible for a teacher to make the thing easier. So you need to try your own in the way that I am prescribing here, and you need to once you need to try, I hope it will be easier. I am trying to make the things in an easier way, and again in between, if you feel that the things are not going easy and you are trying, provided you are trying, and if you are failing after your try, I am always there to extend help, any amount of help you need to understand the course. Anyway, so here let me give you a home task here, that a function f is both convex and concave if and only if f is affine. Can you prove it? Let me give you a quadratic function with positive semi-definite Hessian half x transpose qx plus a transpose x plus b. So here if q is a positive semi-definite, by this inequality will mean that q is positive semi-definite. For a positive semi-definite q, a quadratic function is a convex function. Ninth example is an interesting example. It occurs in the problem of least square with ax minus b square, where A is a matrix of real matrix of order m by n, and x is the variable n dimensional, and b is a vector in Rm. Fine. This is the function fx is equal to ax minus b square. This is always a convex function. that you find the Hessian of this function, and the Hessian is positive semi-definite. Can you be able to prove it that the Hessian of this function fx is positive semi-definite? Try to prove it, and in a later day I will prove that if a function is having positive semi-definite Hessian, then the function must be a convex function, and therefore that will verify that a least square function is always a convex function. The last but not least, let me give you the function logistic loss function. Logistic loss functions are given by the expressions like log inside 1 plus some exponential function. Let me consider to do a minus x here, and this function you can just graph out and you can be able to find that this is a convex function. So all the examples, all these 10 examples, the expressions, although everywhere I have not written those are convex, but they are all convex functions. The concave ones I have bracketed and I have mentioned them. Fine. So on the next day, then in the next lecture I will continue the discussion with properties and characterizations of convex functions. We note that checking convexity is not an easy task. The inequality is not always easy to verify, and therefore several convexity preserving operations, several properties, those must be satisfied by convex functions must be derived, so that with the help of those results we will be able to check the convexity of the functions, and those will be discussed in the next day. In the next lecture our agenda will be discussion on the properties and several interesting characterizations, zeroth order, first order and second order characterization of convex functions. By zeroth order I mean where the derivative of the function will not be used. By first order I mean only the first derivative, only the first order derivative of the function will be used. That means the gradient information of the function will be used. And in the second order characterization, the Hessian value of the function, Hessian matrix of the function will be used to check the convexity. Well, so on the next day, the agenda is properties and characterizations of convex functions. Well, so let me stop here. Thank you. Thank you all for your kind presence.